Okay, we have something kind of quick today. What I want to do is go over the recurrence relation of the Digamma function. So we have this formula up here at the top of the board that says the Digamma function is z plus 1 is going to be the same thing as Digamma of z plus 1 over z. And what I want to do is kind of relate this to what we have here for the gamma function. And really this here is just our factorial relationship extended beyond the integers. Like if this value of gamma of z plus 1 is just going to be z factorial. And then over here, we can write this here as z times z minus 1 factorial. So this right here is going to give us a similar relationship for the Digamma function that allows us to reduce this from z plus 1 to z. But this is going to be pretty easy to show just using our formula over here for the gamma function and our definition right here for the Digamma function in terms of just the derivative of the natural log of the gamma function. So for our starting point, we're just going to use this again over here, this relationship for the gamma function, writing it like this. And then all I'm going to do on this is let's just take natural log on both sides of the equation, take natural log here. Then on the right side, by property of logarithms, I can break this up and turn this into an addition. So I can write this as natural log of z plus natural log of gamma z. Then all I want to do with this equation is just differentiate on both sides. So start on the left. So starting on the left, we differentiate natural log of this. We're going to get 1 over gamma z plus 1. But then we do need the chain rule on this. So in the numerator, we're going to have the derivative of gamma z plus 1. Then over on the right side, this is just going to become 1 over z. We're differentiating here with respect to z, so the chain rule is just going to give me another 1, so we'll leave that off. And then here, same kind of thing as this. Derivative of this is going to be 1 over gamma of z. Chain rule gives me gamma prime of z. But this right here and this right here are exactly in our form. So we can write each of these as the Digamma function. This one just z, this one of z plus 1. So just like that, we have our formula, because on the left side here, we have Digamma of z plus 1 is going to equal 1 over z plus Digamma of z. So that's about it. You just have to remember the chain rule on it, because let's just remember the gamma function is going to be an integral. And so also I think we saw it in another video that the Digamma function can be expressed as an integral, because if you differentiate this, basically you can use Feynman's trick on it and it becomes like an alteration on the gamma function. Because if the gamma function, what's our definition for the gamma function? It's going to be the integral from 0 to infinity e minus t dt x to the z minus 1. So just real quick, if you differentiate this and do Feynman's trick on it, I'm not going to do it out, then what's going to happen is you're going to get an extra term right here. You're going to get a, I've got my variables mixed up too. I think this needs to be a t. There's no x in this. So if this is t, if you differentiate this with Feynman's trick on this, then differentiating with respect to z, t is a constant, and so you're going to get a natural log of t in here. So then knowing gamma prime of z is going to be this thing. To get back to the Digamma function, all we need is this part, so you can just divide in the gamma z, and then you get your Digamma function. Anyway, that's it for today. Thanks so much for watching. Have a good day.